rewarding sort of job where I get to present a lot of the work that's done by the community and kind of get to take credit for some of the work that's happening. Now, one of the projects that I have been investigating a fair bit recently is this one about unikernels. Now, at the outset, I will tell you that this presentation does not have any mentions of AI or OpenShift, which seem to be the running thread through all of the talks that I've been to here. But anyhow, there is a bit of history between Red Hat and unikernels. We'll talk about that a little bit. But also, unikernels in general as a technology seems to be in and out of the news a lot. And so, I've been investigating this a little bit from the time I heard about it in like CNCF and Kubernetes events and context. But the application of unikernels as a technology seems to be a lot than just the cloud or just for very specific types of computing and applications and things like that. You can probably guess what this is from the name itself, but I'll dive into a little bit of detail about what this is as a technology, what it means for the community at large, and some of the ways in which people are taking advantage of this. And I'll obviously close out with like some demos and showcase of where you can get started and how you can go about doing this a little more. So back in the day when computers were extremely hard, they did not come with an operating system necessarily. So the fundamental foundations of computers did not include the notion of an operating system. At the moment, some of us can't even imagine that as a possibility. Now this, what you see on screen is a Honeywell H200 or 500, something like that. And it made use of like punched cards and tapes and things like that. And they only came with like an application. And that's all you basically needed. There was a person who took care of scheduling and sharing and sharding and all of these other things that modern operating systems do. And I'm not saying that's the way to do things, but there's probably a little bit of truth there that is worth emulating. And what we have today largely begins with this notion of what are called virtual machines. And everybody who's using any kind of cloud service, for example, whether it's a bunch of like Red Hat stuff, the AWS stuff, the DigitalOcean stuff, some Google, Azure, what have you, we're all effectively interacting with the virtual machine or the hypervisor technology effectively. And virtual machines have a very well-defined architecture. Now what they do is they allow you to host applications with their own operating systems and things like that over an abstraction that they like to call the hypervisor. And like diabetes hypervisors come in two flavors. There's like a type 1 and a type 2, and there's so many things there. That's kind of outside the scope of it. Let's leave it at that. And irrespective of which hypervisor type you're using, the idea is that underlying hardware gets utilized better. The applications that run on top of this hardware are well isolated, a little bit more secure, they can perform well, etc., etc. So all of the marketing benefits are quite clear. And then came along this technology that said, hey, there's a somewhat better, and by better we mean slightly more performant, slightly more secure, and slightly better in terms of managing your applications in the cloud remotely. And we just want to package it somewhat differently. And that's what we call containers. And containers as a technology is rather old, but it's really what we like to, it's what we mean when we say Docker. So Docker came along, changed everything about containers. They basically built a fantastic developer experience and allowed a lot of people to take advantage of what are essentially C groups in Linux that allow you to isolate applications and things like that. Containers were a match made in heaven for VM-based infrastructure. So if you package things into a container and were capable of running it on a virtual machine, you are golden. That covers like 90% of all of your infrastructure headaches and all of the problems associated with your infrastructure and your applications in production and things like that. And so containers on VMs became this very popular way for people to package their applications and deploy them. Now, we all know what that looks like. A lot of people are better qualified here probably to talk about containers and do containers well. And then there's this new family called micro VMs. The first I heard of this was when AWS Firecracker became quite popular. And then there was another announcement about 3 months ago with Microsoft launching Hyperlight. So that's another family of like micro VMs. And what they mean by micro VMs is it's just the concept of a virtual machine, but like the virtualization layer is much smaller in terms of what they're trying to accomplish, general purpose, and then it's also spread out or like contained individually and isolated individually as a virtual machine abstraction that you can deploy along with your individual virtual machine, as opposed to having a broad common hypervisor layer. This is a much smaller footprint in terms of the abstraction itself. And now, in the same vein, what we are going to talk about in the next 20 odd minutes is take this notion of the application requiring a kernel running on an operating system abstracted by the hypervisor over the actual hardware. You replicate that application 100 times over. This is what your common thing is. But your operating system is a massive overhead for every VM/container/other architecture that you create. Now, what proponents of the unikernel system are saying is, why not take that bulky operating system and try to make something more efficient out of it? And that's what you get when you try and not necessarily like eliminate the operating system. So this is more of a NoSQL, no ops kind of thing. So we're not talking about no operating system, but we're talking about putting the apps along with the libraries that it needs as close to the hardware as possible. Potentially run it on the hardware, but if not, have a very thin virtualization layer that can work with your application and its library. So it's taking all of the lessons from the VMs world, from the lightweight VMs world, marrying them with some of these successes we've seen in the containers world and recreating them as unikernels. So it's about eliminating that bulky operating system, and then what comes as a result is you have a virtual machine like image, but then it is specifically meant for running a single application. So it's not a general purpose operating system, or you can't think of unikernels the same way as you think of VMs or containers and things like that. Containers work for a broad set of languages and frameworks, and unikernels likewise work for a broad set of languages and frameworks, but at a given point in time, they're meant to work for a single application. It's single process, but it's multi-threaded. Okay, so it's not like it doesn't have concurrency or any of those things. So I was once giving this talk, and then somebody just couldn't accept that there exists a modern framework that doesn't do concurrency. No, so this is a multi-threading is available, concurrency is available, but it's a single process framework, and it's meant to function for a single application at a time. So that's one of its big limitations, but we'll explore that in a little bit more detail. In reality, it looks tiny because application code doesn't take up a lot, and when you eliminate like the bulk of the operating system, that also doesn't take up a lot. Apologies in advance for a rather deep Linux lesson on a Saturday morning, but we're at a developer conference and um, this should not be off the table. So I'm not sure how many people are aware of privileges in the Linux kernel, but if you're not, then the set of concentric circles will somehow illustrate that concept. Now, what this means is you have different kinds of applications that run on any Linux machine. So for a very general purpose machine as this, the one with a lot of stickers, there's a ton of applications that run in what is known as user space. And this user space is isolated from what is known as the kernel of the operating system through many layers. And so in the Linux world, these are called rings. So ring 0 is the central kernel, most privileged part of the operating system. And then you move outward figuratively in order to have many more layers that actually run their applications in different spaces with more reduced privileges as you move away from the kernel. Now what unikernels aim to do is run your applications and things as ring 0. So in the most privileged mode, they'll run that. The reason they do that is if you eliminate a lot of these system calls that happen in the middle, you're capable of getting so much more performant applications. I kind of knew this diagram would throw people away, but still. So let's take another example. So this is an example of an Nginx server that people will run, and a lot of the libraries that you find in any general purpose operating system are unused. Now what does the stack look like? So the stack is, there's a user application, there's the kernel beneath everything, and then there's a bunch of libraries and services in the middle that are required for applications to run and function, but are largely unnecessary because this entire design and architecture is meant for accommodating a large number of applications and being general purpose as opposed to being purpose built or specific. This is what Nginx would look like in some kind of comparison to what Nginx actually requires to function as a Linux-based server, let's say. So how do you transition your operating system and the bulk of your non-application code into something that's more lean and something more efficient? So that's the pursuit that we are in today. So at the base, what we require is something that defines the platform on which I'm going to build, and something that defines the architecture that I'm going to use. So these specific things define a lot of what is going to be built over and above it. Now after that, you need a bunch of different things to service anything that needs to function on that hardware. So you need something like a scheduler, you need some console, you need something to do memory allocation, you need a file system, and you need some networking. So these are examples of the libraries that actually perform these functions in a standard POSIX compatible architecture. Okay, and then you put the language specific libraries and runtime you want, and effectively you're creating the bare minimum that you need in order for a functional stack. So you go from that big bulk that we saw in Nginx, for example, and this is the bare minimum that you need in order to run a functional Python application on any stack. All right. So is it possible then to make an operating system plus application layers plus all the drivers in between plus the services and things like that at a very small size but yet fully functional? So that's effectively what a Python unikernel will look like. We've all been to this store. I'm not going to name it because that might be pandering, and they're not a sponsor. So maybe when they do sponsor DevConf in the future, but it's ideally picking what you want, layering it on top of your a certain base, and then making use of that in order to consume it. This is what the overall spread looks like. So if you're talking unikernels, your general purpose operating system has all of these different things, okay? So it has many libraries of what you can include or what is required. And then, like I showed you before, there's something that's specific for every architecture, something specific for every little platform out there. And then you're all aware of like drivers and networks and file system, blah, blah, blah. And so depending on what you choose in the bottom, you make specific choices on top. And then once you include the runtime, you get that very specific stack. And so this emerged from a, I think, 15-year-old concept called library OS. So library OS allowed people to define very modular ways in which you can pick and choose what you want from a larger operating system. So it essentially maintains this ethos where an operating system is a library of different components, and then you pick and choose what you want. So pretty easy. And so as a result of what is known as a build process, you get what are known as unikernels that are specifically made for a language to run on a platform. You can already tell what the downside can be from this. So if you wanted to do a Java application, not many of you might be that old or that bored. So if you wanted to do a Java application, for example, you have to rewrite your unikernel for Java for that architecture. Let's say you're very hipster and you do like Raspberry Pis in your basement. Then you have to rewrite your unikernel for that language in a different architecture. So you can already tell that, how many do I maintain and how do I write things. And this was one of the big reasons why unikernels never became very popular. There wasn't a developer experience out there where you could say, hey, let me go in, start writing these things, and then have something like a quote unquote Docker file where I can change some of the meta values, and then it will spit out another image for me, and then it'll spit out another image for me, and then I can make use of that. So none of that existed until very recently. And so in my opinion, that's been something that's held the unikernels community back significantly. So you had to be a very competent Linux person in order to get a unikernel built, let alone be able to run it and debug it and things like that. People have heard of WASM? Yes, no, maybe. Yeah, so it stands for Web Assembly Modules. They somewhat replicate a lot of these ideas in terms of how to make a large set of applications useful and runnable on the cloud, etc., etc. So they're also like language specific and things like that. So you compile WASM binaries that are specific for a language, and then if you want to do another WASM binary, you compile it in. You compile another binary essentially. So I like to draw this as a parallel. So a lot of people who understand WASM will understand unikernels better and vice versa. But anyhow, the focus has always been on what is known as isolation. So isolation in terms of, can I get my apps to run completely in the smallest unit of compute as possible. So they made it possible with VMs. It was a pretty large footprint. Micro VM somewhat smaller. Containers took a different approach. WASM takes a different approach, and unikernels sort of, I think, marry this notion of being lean with and purpose built with being able to run on something as general purpose as VM. So isolation is a big reason to use unikernels, and they achieve it with remarkable efficiency. And then you have to understand what is a user mode versus a kernel mode in order to appreciate unikernel's advantages. So like I said, user mode is when you run your applications in ring 3. Okay, kernel mode is when you run them as ring 0, and you get, again, remarkable difference in performance when you do one versus the other. And we've all heard these terms before. A function call is when you do a function call within the scope of a program or an object and things like that. System calls, same thing. a remote invocation, but across the system. And so imagine having, so system calls are always much faster than function calls can be. And imagine replacing all your function calls with system calls. And that's effectively what happens when you go from like a ring 3 situation to a ring 0 situation. So you get a much faster response for all of the calls that you make because you're that close to the hardware and you have so many less hoops to run through. Now, all of the security folks will have alarm bells ringing and things like that. Whenever I say this, there's merits to this approach. There's some demerits to this approach. But with sufficient observability and monitoring, you can prevent a lot of malicious actions because you avoid like big chunks of the operating system itself. There's very little that attackers can do. So you remember how I said this is a single purpose entity. An attacker often comes and runs a program that's parallel to the one that you're running. So you have an application and a malicious actor attempts to run another application or do some traffic egress and things like that. In unikernels, you cannot run another application. So unless you exploit some backdoor on the application itself, you don't have to really worry about security. And you have if you have something exploitable on the application, then you have so many other things to worry about than security. So this is an example of the architecture for one of the more popular unikernel teams that are there right now. It's called Unicraft. It's an open source project. It's somewhat of a modern take on unikernels. Check it out. It has all of the different pieces that I spoke to you about a little while ago. And then I'll come to like the most embarrassing part of the presentation for me while I was making this. I've spoken about a lot of the advantages that unikernels can have, and it all boils down to like 3 things, which I think is for every single application that people talk about. Talk about Kubernetes, people will say, oh, it's portable, it's performant, it's secure. Talk about hypervisors and VMs, people say, oh, it's portable, it's performant. Talk about, I don't know, what's the latest Rust or TypeScript, Haskell. They'll all talk about, it's very portable, it's very performant. So I hate making this slide, but, bottom line, unikernels do promise these 3 and do deliver on them. So, size is a big thing for us, and good things come in all shapes and sizes. There's a massive market out there for things that are big, things that are medium, things that are tiny, and unikernels take this notion of, again, just to reiterate, what is the bare minimum that's required and build a functional unit on top of it. Now, what really surprised me as I was researching about unikernels is it goes back a long way. So this is like a 90s thing where people, the first evidence of the concepts of jettisoning an operating system and keeping things lean, that emerged. And then a few years later, we had public demonstrations of all of these different ways in which you could do unikernels. Like HAL VM, for example, the one here, was meant for the Haskell community. So they had a language-specific construct in order to construct unikernels and things like that. And then there was evidence of more general-purpose platforms you could use in order to do unikernels, and all of them were in pursuit of smaller, better virtual machines, because the VM things were catching on at that time. And then there was another JavaScript specific framework that emerged in the 2010s, and the first evidence of the library operating system that we spoke about came along. And then fast forward a few years, there's a my only Red Hat mention. So thank you for being wonderful hosts at this event. But there is a Red Hat unikernel that still exists, and if people want to pursue that, you're more than welcome to. And my first introduction happened with Unik, which is like a cloud foundry platform, and I work as part of that community a lot, and they were the first ones to show evidence of a platform for unikernels and things like that. And right now the big bet is on nano VMs, which takes a slightly different approach from library operating systems, and Unicraft, which takes the library operating systems primitive and builds on that. Very recently, there was also evidence of functional unikernels on Kubernetes, and there's a project called urunc. So unikernel runc. So runc is like container runtimes. Urunc is a container runtime for unikernels kind of thing, and that's when it caught my attention big, and they're demonstrating the value of unikernels in platforms that are adjacent to it. What's going to be the big thing this year? I don't know. My talk on unikernels, obviously, but other than that, it's waiting to be discovered, it's waiting to be used, and it's waiting to be exploited. Let me run a couple of quick demos. I don't have a lot of time, but let's make the most of this. So this is a demo of running nano VMs. So nano VMs, like I said, was one of these technologies that just run, and we can fire up a browser. What did I do wrong? Port number. There you go. So if you look at what's here, there's this command called ops, which is how you orchestrate nano VMs, you build them, you deploy them, etc. And then there's a JavaScript file, and then you basically use this node image. So here's where it becomes like containers for a bit, and that's the better developer experience that people are purporting. So it takes a node image, it loads the JavaScript file there, it creates a node server, and it serves it, and it does that in milliseconds, and it just takes 2 seconds. Even if you put this on a cloud server, you can get a cold start of under a second, and so it makes it extremely useful for serverless applications, for example. So in this catalog, I have tons of examples. Let's do I don't know. Hopefully this works. So what unikernels do in the Unicraft world is they define what's called a craft file. They also use Docker files adjacent to this, and if you look at this, from scratch, this is a multi-stage Docker file. So essentially they use GCC as the base layer to build and for file systems and things like that, and then they'll only copy these layers onto the final unikernel. So we can try this, and so it will build that unikernel for me, and then it will allow me to run that unikernel. So this is a slight deviation in, okay, maybe I should have picked a different one. Let's see. So this is a slight deviation from that old notion, but it's a much better developer experience overall. So while this builds, there's definitely adoption problems, and like I said, developer experience around building unikernels is like the big one, and there's companies that are tackling that. So if there's also a thing about why unikernels are unfit for production that outlines a lot of the things that are bad. This is an article that's about 5 years old. A lot of things that were mentioned then have changed now. So there's better debugging, better support for all of these things. Now, my big pitch to you is, in a world that's obsessed with unicorns shitting rainbows and things like that, there's some fundamental technologies that I believe people should be aware of in terms of containers, in terms of infrastructure, and in terms of how you can create the infrastructure on which things can be built. So that's my big reason for giving this talk today. Thank you so much for being such a patient and nice audience. And thank you DevConf organizers for having me. That's me on social media. If you want to say hi, please do. Don't be a stranger. I'm more than happy to engage with folks in the community. If you have any questions, I don't know how much time I have, but I'm happy to take them now. Yeah.
So what I observe from real world means any product should be adapted by mass should be very user friendly.
Sure.
Okay, like container, any application which are built on a container, and another user want to deploy that, that is very user friendly if you know. It means if you think,
Yeah.
because and that person doesn't know that how to build a container, that is also fine.
Sure.
He just can deploy that.
Sure.
But in order to adapt this unikernel by mass, uh, that person should be very tech savvy, I think, because how they can select that those kernel files, kernels. You got my point. That
Yes.
binary.
So this is the story of 5 years ago, roughly. So before, say, nano VMs existed, as a company and as a community, people had to cobble things by hand. But if you check out nano VMs, go to their GitHub or like their website and things, you'll find they have a library of unikernels that you can pick up and deploy. So, like I said, all of these companies that want unikernels now and in the future are advocating a Docker-like approach where there's a unikernel available for what you want to do, but you can't just go to a unikernel hub like Docker Hub, for example, because as a technology, it's supposed to be compiled for your application. So I can't have your application specifically available. I can have a Redis unikernel available. That's easy. It's already possible. But I can't have it for any application that you want. So let's say you want to write your own kind of messaging queue on top of some Kafka thing that's available or some consumer. So your unikernel will be, you'll have a Kafka unikernel, but that will only be like the middleware of sorts. But for you to be able to consume that, you need to create your own unikernel. And so what's being done is bring your own application kind of approach. So bring your application, have these unikernel base image layers kind of thing, and then compile it. So some simplification is being done, but it can never reach the kind of experience like we have in Docker Hub, for example. So even there, it's like you have to compile your application into an image, right? So you're effectively doing what you have to do with unikernels a little bit, but the overall experience around it is changing. So yeah, your point is well taken. People are working on it.
And there's one more thing. You said that another application can't be run. An attacker can't do that thing. But somehow means some application needs another application to be run at the same time. What that will?
They're all remote calls. They're all remote calls. So just this example that we were talking about. So you have a Kafka, let's say, you have your application that consumes this, and then you have a third service that does something else. You'll have to set up remote invocations across these as you would with any microservice-based architecture.
Thank you. Thank you.
Nice.
Nice to know.
Hello. I have two questions. First one is, as if we put containers and unikernel based machines side by side, then how much efficiency or cost saving can we expect?
Without knowing what the container is and things like that, it's hard to say. But just in terms of comparison, a container typically, from what I've seen, is about 300 megabytes and things like that. A unikernel will be like 300 kilobytes. So you can pack 1000x more unikernels in the same space that it would to do a comparable container. So that's where the efficiency stems from. And so there's some benchmarks that Unicraft have run. So if you go to unicraft.org, I think, and look for benchmarks, you'll get some of the answers that you want.
Okay. And my second question is, like, in the demo, we have built x86 based, we have run the container for x86 based machine on and compiled it on same architecture. So it's cross architecture compilation possible. We need another machine for that also.
Yeah. No, you can definitely compile other architectures on runners. Obviously, you can't run them. That's it. Yeah.
Thank you.
Yeah.
So with unikernels, right, I understand that the attack surface becomes lesser and all of these advantages are there. How do you compare distroless images where you actually have a thin OS image in terms of even the same question, in terms of sizes, if you've done any benchmarking or if you have witnessed anything, compared to unikernels? And is it too much of an overkill to use unikernels compared to distroless images? Because we would rather, we all know that this is only in runtime.
Yeah, I was just going to say, there's a very compelling case for distroless images because of the entrenchment in the container ecosystem right now. Unikernels and distroless image stem from the same truth, which is let's not put anything unnecessary in an image. Let's not put anything unnecessary in the operating system, etc., etc. So there are just two ways in which you are accomplishing effectively the same thing. It's just for very different artifact types. On the one hand, you have VMs that are tiny. On the other hand, you have containers and container images that are pretty small and a fraction of the size that they need to be. So in terms of the purpose that underlies both these activities, it's exactly the same. So I 100% advocate the use of distroless images. Just in terms of comparing footprints, I would say unikernels will still remain smaller and will help you push that to its maximum limit. So if you're getting, let's say, 5x kind of efficiency with distroless images, you're going to enjoy like 100x, 1000x with unikernels. And so, but distroless images are capable of accomplishing much more than a unikernel can. So if you have multi-process applications and things like that, unikernels are not going to be suitable for that. You're better off doing distroless images. So unikernels is not like a one-stop solution for everything that needs to be slimmed down and made small. There's a lot of these problems for which distroless images are the right solution. So they're both different classes of problems if you want to think about it.